All right, thank you for the introduction. I am Darren Vengroff, and I'll be talking about impact charts. So just a quick agenda. I'm going to give you a real brief background, talk about kind of what the problem is that we're trying to solve, go through the methodology behind impact charts, show you sort of some validation with synthetic data, demonstrate that we can sort of find Easter eggs that we plant in data. And then I'll talk about very briefly how you can use the open source package to generate impact charts on your own data sets, and finally go through an application on some real data where we were able to find some effects that traditional, for example, regression techniques are highly unlikely to find. Okay, so background, sort of this work really brings together three areas. So, machine learning, which in the traditional sense tends to focus on problems of prediction, right? So what video would someone want to watch next, or who's going to be able to pay back a loan, or in the LLM case, what word comes next. Statistical social science, which has been around for longer, has sort of a different focus. They're more interested in explanations. So, does going to college lead to higher income, or are black people discriminated against in access to credit? Causal models, which we heard about in the last talk, are kind of the gold standard in many cases, but regression methods are still very, very widely used, and literally tens of thousands of papers over decades have used them. And then the final thing that we'll bring into this is interpretable machine learning, which kind of evolved from the question of in many cases, of whether there's bias in machine learning systems. And to answer that question, techniques were developed to sort of explain, well, why exactly was this prediction made given a particular input? So we'll see all of those come together in this work. And the focus, though, is really on, of those three, the kind of social science problem. We're not trying to predict things here. We're trying to offer some kind of explanation as to what the relationship is between one variable or another. The other nice, interesting properties of these, they're non-parametric, so we don't have to know we're looking for a linear effect or a quadratic effect or whatever it may be. They also allow a lot of different notions of error and don't make a lot of assumptions. So, when you first learn regression methods, you learn about heteroscedasticity and how important that assumption is. And then, you go into the field and actually start using it, and pretty much everyone forgets about that and ignores it. So it also conveniently works really well on aggregate data. In fact, our real-world example will be on some aggregate data at the census tract level. So it doesn't have nearly the risk of exposing, the privacy of individuals in the data set, or it doesn't require data sets that have that kind of exposure. Okay, so let's jump right into the problem. The problem is just very simply, how is some target variable y related to any one of a series of features? I'll use the machine learning terminology here, xi. So, we typically have our x's in a matrix, so we've got the features are the different columns here, and then we've got some n number of observations. Those are the rows going down here. And then we have a corresponding n observations of the y's, right? So we want to be able to say something intelligent about, x3 has no effect on y, or, x7 as it goes up, y goes down, or that sort of thing. So one of the things we often do before we start with any real techniques is some exploratory data analysis. And here I'm showing a scatter plot, which is a common thing at this phase, where I've got, in this case, x3 along the horizontal axis, and I've got y here. And so, if there's a very strong effect of x3 on y, I might see a trend there, visually, and sort of have a very quick idea where I want to go with it. I don't really see one in this data. So it's fairly unsatisfying. There may still be something, it may be a lot of noise. So maybe the next thing I try is some regression methods. So, I did some linear regression here. I did a quadratic regression. R squareds aren't great. That sort of depended on what field you're in. Some fields, these are not terrible R squares. Other fields, they're downright awful. But there's still, there's really no clue, and I certainly don't visually sort of see like what's going on. Does X3 have any impact? Maybe it has an impact, but other things impact it more. There's so much noise in the data, how I gathered it, that it's overwhelmed. So what if instead we could see something that looked like this? And here, this isn't a scatter plot where I have y on the vertical axis. Instead, I have something that, for the moment, I'm calling impact on y. And I still have the x3 on the horizontal axis. And so what this chart is trying to convey visually is, for various values of x that I've observed, how much did that affect the value of y, relative to if I didn't know anything about what that x was. And so over here where x3 is negative, I'm basically saying it maybe has a very small negative effect. It maybe drives it down a little bit, but it probably, it doesn't look like it's doing much of anything. Whereas when x3 becomes positive, it starts pushing y upward in, maybe this is a quadratic or cubic or, possibly even exponential. But it's definitely showing me that there's, some effect on the value of y that I can trace to the impact of the values of x3. So, as I said, it would be nice if we could do something like this. We can, it turns out, or I wouldn't be showing you this to motivate the rest of the talk. So let's talk about the methodology behind how we might actually construct something that looked like that. So, super simple explanation for those familiar with interpretable machine learning. We're bagging Shapley values, but the longer-winded explanation, which I'll go through in the next few slides, is we're going to build a series of independent machine learning models. We're going to build K of them, typically for maybe K is around 50 or 100 or so. We're going to train each one on a sample of the data. So we're going to keep resampling over and over again and fit each model on a different sample. So those models will, give different predictions. They won't all agree because they weren't all trained on the same data. And then we use something called the Shapley value, which has actually been around since the 60s, but is in the past 5 years or so become a really popular way of interpreting the impact of features on predictions in machine learning. And we're going to use that as a measure of our impact. And we're going to do that, independently across, again, this whole ensemble of models. And then we're going to plot the distribution of those Shapley values. And as we'll see visually in the next few slides, that's going to give us some notion, if we construct the plot properly, of what's going on, like in the last picture I showed. So here's how we do it, sort of step by step. So we've got our n observations of our x and our target y. That's what I showed you earlier. And I'm going to take a random sample of that, right? So I'm going to take just the yellow rows here, and then I'm going to use those to fit a model, right? In this case, it's a random forest, maybe, or a boosted tree model there. And now I'm going to go back to the original data. I'm going to take one observation of 1x. So that's just blue highlighted one here. And I'm going to compute a Shapley value that's going to tell me how did that one observation affect the prediction that I would have made for the row that it was in. In this case, it wasn't even in the sample, but it doesn't matter. Sometimes it's in the sample and sometimes it's not. Then what I'm going to do is I'm going to repeat that k times. I'm going to do it again and again for each model. I'm always going to use the same blue observation here. And I'm going to plot these impacts vertically. And so what I see here, here's the impact in the first model. Here, the impact in the second model is a little bit higher than it was in the first one. In this very last one, it's lower than the other two. And what I'm going to do is align those all above each other, plot them vertically like this, and you can see I get these gray dots give me kind of the distribution of what those Shapley values were, and then I put a green dot at the mean in the middle. So I'm essentially saying, for all these models, what does the distribution of the Shapley values look like? And then what I'm going to do is I'm going to repeat that for all the observations of that particular feature x sub I, and I'm going to plot those vertical distributions on a horizontal axis whose value is the value of the observation of xi that produced that distribution. And so what I get here is I get a bunch of these green sort of, the ensemble's overall estimate of what the impact was, but I also get a nice representation of the distribution and sort of the variance around it. So here I sort of see for low values of this x, as x increases, y tends to be driven upward, and the bounds are pretty tight around that. I can be pretty confident there. Whereas here it starts to level off. It looks like there's not so much of an effect anymore, but the error bars are much wider. The distribution has much higher variance. So I'm actually less confident of that really being the effect over there. Right, so, okay, I just used a bunch of techniques, concatenated them together. Did this really get me anything that resembles what's going on in the data? So one way to find out if that's going on is to generate a bunch of synthetic data where I know the ground truth. I know what the effects were and say, well, does this method tease them out? So I constructed, for this example, a synthetic data set. There are 5 different x's, and the y is a sum of 5 different terms, one based on each of the x's. Actually, the last x, it doesn't do anything, but the total value of y is the effect of x0 is linear, the effect of x1 is quadratic, then I've got a sinusoid, an exponential, and then I've got sort of a dummy variable x4 that has no effect at all. And so I generated I generated a distribution randomly of a bunch of x's, computed what the y is, and then plugged it into my impact chart generating code. And here's some examples of what I got. So this is that very first impact chart I showed you before, but I've overlaid on top of it with the orange line. That is what the actual data was. So you can see that, at least in this synthetic case with these embedded Easter eggs, it found exactly what I put there. Same thing for a linear one. And I forgot to mention there's also some noise added to the whole thing, some Gaussian noise. But so for the linear one, I get to do a pretty good job. The quadratic one, I see the shape. It's not quite perfect. I find the sinusoid for the periodic effect that I had put in my data set. And for the variable that has no effect, I got a flat line at 0. Nothing was detected. So at least in synthetic data, I did a pretty good job of being able to find the things that I hid in the data, and ideally wanted to find what their effects were. So how did I do that, or how can you do that with your own data? Very simple. It's all in GitHub. You can pip install the project. I'll put that QR code up again at the end for anyone who doesn't have a chance to get their phone out fast enough to take a picture. But once you've done that, it's 3 to 5 lines of code. 5 if you count the import and the line of code that gets your data from wherever your data lives. But really you just say, in this case, there are several different implementations in the package, but in this case, I'm going to use one that uses XGBoost as its underlying model. And then I'm going to fit that. By default, it'll do some hyperparameter optimization as well. I can turn that off if I want to, and use whatever default or parameters I want. And then I just say, okay, give me all the impact charts, and it will generate one chart for each X feature. They all look like the ones I just showed you, and I can sort of see what's going on in my data. So let's look at a real-world example, right? It's great that we can find synthetic effects. It's unfortunate in the real-world example we don't have the ground truth to compare it to, but we can look at it and sort of see, to someone who has domain expertise, does what comes out of it make sense? So the example I'm going to show today is eviction data. So the Y that I'm looking at, the target variable that I'm trying to understand what affects it, is the rate of evictions. So within, in this case, a census tract, for every 100 renters that live in that census tract, how many of them are evicted over the course of the year? In this case, in this data, it's how many times did landlords file eviction cases in court. They don't all finally lead to an eviction. This data is gathered over 10 years in DeKalb County, Georgia, which is in the Atlanta area. The features that I'm looking at are economic, median household income of renters. You would expect low-income people to be evicted more and higher-income people to be evicted less. Seems like a reasonable hypothesis. And we also put in features for race and ethnicity. So this comes from U.S. Census data. We put in, a feature that is, for example, the percent of the renters who live in that area who are white. Another feature for the percent who are black, Hispanic, and Latino, and so on. The eviction data came from the Princeton Eviction Lab, and we again used XGBoost with 50 models and 80% samples to do the training. So here's what the impact chart looks like for that data. We see that this is, in this case, the feature we're using is median household income for renters. We threw out people who are homeowners because they're not necessarily going to influence this. And if I look at the purple area, so this is, remember my hypothesis, sort of, initial hypothesis was people that are lower income are going to get evicted more. The very lowest income people, the impact is actually negative. You can see it's down, somewhere in the -5 range. These people, even though they have the very lowest income, they get evicted about 5%, 5 percentage points less than similar people of other incomes. And you talk to an expert in this field and they'll tell you, yeah, that's because people in that income level qualify for the very limited number of social programs. They may live in public housing or senior housing, and the rules in those spaces don't really allow as much eviction. Whereas the orange area, that's the working poor. That's people who are working 2 or 3 minimum wage jobs. They don't qualify for those programs I mentioned. They are at the mercy of private landlords, and they get evicted like crazy. they're a few days late on their rent. It depends on the jurisdiction, but a few days late on your rent, eviction proceedings start. And then once you get up to the middle class and move up, it's flat. There's not really much effect of income. So, we found an effect. We didn't know the shape of this in advance. We didn't really have any domain knowledge, but validated it with domain experts. The super interesting thing that we found in the case of this county, we've done this for almost 500 counties, but I'll just stick with this one example. We had the race and ethnicity variables in there as well. So I'll look at another impact chart. And the key here, first of all, is these are plotted on the same vertical scale, right? So one of the things, the code by default plots them on the same visual scale or vertical scale so you can compare them visually. This is the impact of blackness on evictions. So over here on the left, these are the neighborhoods where less than 20% of the people in that census tract are black. And the impact on eviction rate is, -10 to -15. Very, very non-black areas have lower eviction. Opposite end of the spectrum, neighborhoods, that are 90% or more black renters, the eviction rates are way higher. And the scale here, the vertical scale, the impact of race in this case is 3 times the impact of the economic variables. Now, you repeat this analysis in other areas, and that's part of why we've done this in 500 counties around the country. You'll see some counties look like this. Some counties, this curve is completely flat. Some counties, whether you're Latino or not matters. In a lot of counties, actually, what we saw is the only racial and ethnic variable that mattered is whiteness. And if there were a lot of white people, low eviction. If there are not very many white people, it didn't kind of matter who they were, as long as they weren't white, they were getting evicted. And so, because eviction is very localized, it's subject to local laws and rules and conventions, this also then lets us do a meta-analysis, which is in progress now, to sort of say, well, what local policies are associated with bias in eviction. And there have been certainly studies of the impact of all these variables on eviction in the past, using regression analysis. The eviction lab at Princeton, where we got some of our data, has done a fair bit of this. But we've never been able to see with regression analysis kind of richness that we see in the graphs that I just showed you. Okay, so we've got a paper on this with a lot more details that was presented at the ACM FACT conference last month. It's got the eviction data and several other examples, plus a lot more background on the math. Please feel free to look that up. And then future work, we just heard about causal models in the last session. In some sense, that synthetic data that I put together, this is sort of a causal model there that just adds up those components. We're integrating this with more classic DAG-based causal models and sort of understanding to what extent we can reconstruct those or understand those using this technique. On the software side, certainly based on some of the things we've learned in the tutorials, we're going to make these much more interactive, less static, and then looking at additional application areas where we can apply this technique. If you've got one, I'd love to hear about it. So thank you very much. There's the GitHub where you can find the code and more instructions on how to use it. And I'll be happy to take any questions.
I have to get through a maze, sorry.
So, very interesting talk, thank you. I was wondering, how strong of an effect size does it have to be for the method to pick up this impact, have you looked at things that might be more subtle effects? Because it seems like eviction is something very strong, and you can easily see the difference between the two groups. But maybe for, say, gene expression, have you looked at something, how it does at those more subtle levels?
Yeah, so that's a good question. I think when we look at different size of effects, the thing that we've been able to get out, and we haven't, maybe done a fully rigorous analysis of that, but those error bars that are sort of implied by the distribution, that really helps us out a lot, because you're essentially, in cases where, you see a big effect, but you see an even wider distribution on that, and like it crosses zero, you're sort of in the mode where, well, I can't really say anything anymore. And so that's how we deal with sort of order of magnitude or different size effects. You either, if you see a small effect, but the error bars are really small, great, awesome. If you see a medium effect, but the error bars are giant, it's, you can't really say anything. Yes.
Yeah, bunch of questions, but I'll start with one. I know. So you showed your simulated data and that you could sort of recover, but there were some offsets.
Yeah.
Do you have some idea for if the offset was it related to your resampling method? Is it related to how you're measuring impact with the Shapley thing? Do you know why?
Yeah, and actually, the charts I showed you here, the newer ones are a little better, and part of that was, I'm ashamed to admit it, a bug in the code, but no, so they're a little bit better now, to the point that typically the ends of that distribution, or if you do a larger K, you can sort of say, like what's the 99th percentile or something. Those tend to cross, but we don't have a super rigorous analysis of why we're systematically underestimating certain kinds of things. It's an open question.
Hi, I see this very useful in some statistical methods, such as design of experiments. Is there a way where you can see if there's a difference in impact with multiple variables in practice? So I see you represented multiple variables separately on one dependent variable, but seeing a combination of those two and how that impacts the dependent.
Yeah. So there's a couple of ways you can do that. If you have a hypothesis, for example, that the effect is, say, the difference or the product or whatever, you can add an additional variable that you compute that way and then sort of see what its impact is. That's actually worked pretty well in a number of cases we've tried. The nice thing and kind of the reason that tends to work is this approach is pretty robust to extra irrelevant variables. So you sort of throw those things in, and if there's nothing there, it doesn't really affect. It's kind of like the one I showed, the synthetic one, where it was just flat at zero. The other effect that we've noticed, there are sometimes effects where it's more a categorical thing, and so if, for example, in medical data, male patients may be impacted by a drug differently than female patients, and so you can't sort of lump them together. What we found is actually those green dots that here they always showed kind of a nice path. There will actually be two paths, like one above the other, or maybe going different way. And then what you can do is sort of say, well, wait a minute, what ended up on the lower path and what ended up on the higher path? And then you sort of say, oh, all the men were on the higher path and all the women were on the lower path. That's, that we didn't think of that until we saw those kind of separations. And then we're sort of like, wow, that's a really cool way to see the effect of categorical variables.
Sorry, I have to cut off the questions as we're out of time. But please feel free to go and approach the speaker and ask them after the session is over. I think this is the last talk of the day, if I'm correct. So thank you all for coming to this session. We also have one talk tomorrow at 10:45 in the Human Networks track. So please feel free to join that. And let's thank our speaker one last time.
Thank you.